Thanks for joining this learning session today. A while back, I was recruiting different volunteers for a couple of different technical projects and ideas that I had simmering in the back. One of them was around street level imagery. So we've done some experimentation in the past using street level imagery to capture pictures that can be used for potentially disaster preparedness and response activities. There was a blog post linked in the event invite on some of that, where we've used, like in Haiti and Canaan, as that area has been developed after the earthquake, used street level imagery to try and capture the rapidly changing urban landscape. In the Caribbean after hurricanes, using street level imagery to capture the immediate aftermath of a disaster as kind of a baseline data, and also potentially to track changes through recovery. Also, Dale, who I think I saw join the call, was instrumental in American Red Cross in Panama City, Florida, driving around and capturing a ton of street level imagery in the aftermath of hurricane something or other. And that has been kind of the 700,000, I think, plus images that were captured for that are being used in some experiments looking at doing kind of automated building damage assessments and things of that nature. One of the problems that I was hoping to kind of address is how to efficiently task vehicles to collect street level imagery. So you want to be able to travel all the different roads in the most efficient manner possible. So a slightly more complex problem than kind of like the delivery issues where you just have a series of addresses that you want to visit in an efficient order. And so Zade and James are two volunteers who came on and have been looking at kind of different techniques to be able to task vehicles in an efficient manner for street level imagery collection for this kind of analysis. And so I invited them today to share out kind of the work they've been doing, and then invite people to provide feedback and comments and thoughts on what they've accomplished so far. So I will turn it over to them to introduce themselves and give their presentation.
Great, thanks. I'm gonna go ahead and share my screen. Right, so hello, I'm Zade, and along with James, we've been working on optimization of the route inspection problem, and then in particular with applications for, as Dan mentioned, street level image collection. So as a brief introduction, I'll introduce myself first. I'm a third-year undergraduate at Yale, where I'm majoring in math and biology, and I'm mostly interested in pursuing graduate studies, either an MD or a PhD focused on computational biology and bioinformatics. And I joined Red Cross last September to work on this project.
I'm James. I am a second-year undergraduate student at the University of Michigan, majoring in computer science with a minor in biology. And my interest is in volunteering and helping others, especially in the medical field. And I have also been volunteering with the American Red Cross since September 2020. So to start off, we did a little bit of research on the traveling salesman problem. And the traveling salesman problem require many advanced algorithms to create a more efficient estimations, since the traveling salesman problem is not solvable. And the traveling salesperson problem asks, what is the shortest distance possible to travel all cities and return to the original city, given a list of distances and cities? So two ways we can estimate this is using the minimum spanning tree, where we try and find a graph that connects all cities, all nodes or cities possible using the given edges. And this algorithm uses a greedy approach, and it adds the lowest cost edge to connect a new node until all nodes are connected. Another one is a nearest insertion of arbitrary city, where we select a node and insert that node into the route so that the distance between the two adjacent nodes is at a minimum. These two are both heuristics, and they estimate the traveling salesman, and in certain cases, it may not find the most optimal solution. Now I will pass it off to Zade to talk about the graph theory and the route inspection problem. Sorry. This picture is also just another example of the traveling salesperson problem. So we have the red dots as the cities and the black lines as the road. And we want to travel from A, B, C, D all the way back to A in a circle. And in this example, we can see how it may be very hard to find a optimal solution, especially if we have to consistently try each specific edge to connect a new node. Now Zade would talk about the graph theory.
Right, so as James mentioned, like the canonical graph theory problem is the traveling salesman problem, where you have a list of nodes or cities you want to visit, and you want to try and find the best way to visit all of those cities while being as efficient as possible. And to go into more in-depth analysis of these kinds of problems, it helps to make sure that everyone has a good foundation of some key terms that we use in graph theory. So a graph is a structure composed of nodes and edges. These nodes are these vertices, the edges connect two nodes. And when we say we have a path on a graph, we refer to a sequence of edges. So for example, if you go from 1 to 3 to 2, that is a path. You cannot go from 1 to 3 to 5 because there is no edge connecting 3 and 5. So that would not be a valid path. There are some special paths that we're concerned about. For example, an Eulerian path visits every edge exactly once. And a special type of a path is a circuit or a cycle, which is where we start and end at the same node. So in vehicle routing, if you want to start and end at the same place, you're going to be restricting your paths to circuits or to cycles. And we say a graph is connected if we can traverse from any node to any other node. So this graph on the right is not connected, but it would be connected if we added an edge from any of these nodes on the bottom to any of these nodes at the top. When we're talking about vehicle routing, again, obviously having a connected graph is important because for any given trip, you can only traverse wherever roads actually exist. And so one slight variation of the traveling salesman problem, or one alternative, is instead of concerning ourselves with the nodes, we are now more interested in the edges. And the question is, what is the shortest path that visits every edge? So in an example like this, it's quite simple. There's a number of different solutions that are all the same. So wherever you start from, say you start at 1, you can just go in a square. You visit each edge exactly once. We have an Eulerian cycle. This is the most optimal solution. However, this is rarely feasible. For example, even this very small variation, suddenly an Eulerian cycle is no longer possible. Meaning if you want to start and end at the same node and visit every edge, some repetition of edges is going to be necessary. So if you, for example, started node 1, maybe you go to 2, maybe then you go to 4, now you're stuck because if you go back to 1, well, you haven't visited either of these two edges by 3 yet, but you're already going to have to repeat. Likewise, no matter what order of edges you try, you'll find yourself having to repeat at least one edge in order to be able to visit each one. And the reason for this is a key theorem in graph theory, which is Eulers Theorem. And it states that we can traverse through an Euler cycle if and only if each vertex has an even degree, where the degree is the number of edges connected to the vertex. So in this case, 1 and 3 are satisfied. They each have 2 edges. However, 2 and 4 each are connected to 3 edges. And thus we have 2 vertices that do not have even degree, they have odd degree. Now, this makes sense intuitively because if you want to start and end at the same node, then anytime you enter a node, you have to also be able to leave that node. And so if you're going to never repeat any edges, then you must have an even number of edges for that to be possible. Otherwise, if I come into 4 on this edge and I exit node 4 on this edge, then I'm going to have to return to 4 on this edge. But since we have an odd number of edges, there is no longer an edge with which I can pair this edge, where I classify this as an in edge, and then I have an out edge. So if you have an odd number of edges connected to a node, then you're going to have to duplicate one of those. And so the route inspection problem then at its heart becomes a question of how can we optimize this duplication of nodes? How can we basically repeat certain streets or certain edges at minimum cost? So the algorithm then is actually solvable. Unlike the traveling salesman problem, which doesn't have a closed form solution, the route inspection problem actually does have an algorithm that will give you a best solution, which is to first check if first an Euler cycle exists. This is pretty simple using Eulers Theorem. Again, you just check to make sure that all nodes have even degree. If not, you determine which nodes have odd degree. And so there's a special lemma called the handshaking lemma, which says that if you're at a cocktail party, then basically an even number of people will shake hands with an odd number of people, which is another way of saying that we're going to have an even number of nodes that have odd degree. And this helps make some of the computations more efficient, since we know to look for basically pairs of nodes, and we can therefore start matching nodes later in the algorithm. But the idea is then to take this list of nodes with odd degree and then add edges to them to make the graph Eulerian, to make these edges all have even degree. And there are usually a few ways of doing this, which ends up being where the bulk of the computation lies. So one example here, where 2 and 4 are the 2 nodes we need to fix. There's a pretty simple solution here where you just repeat this edge in the middle. Notably, you can only add an edge where an edge already exists, since you cannot, for our purposes, pave your own street. You have to traverse one that already exists. But sometimes the better solution isn't always the one that's just adds the fewest number of edges. If we imagine that maybe the street connecting, nodes 4 and 2, maybe it has a toll, maybe the speed limit is really low, maybe it's just a low quality street that, is otherwise maybe is bad for the vehicle to traverse too many times, depending on what our cost function is, depending on what we're trying to minimize, whether it be distance, time, or financial cost, we might instead prefer to go from nodes 4 to 1 and then 1 to 2. So you'll note that here we increase the degree of 1, but it still has even degree since we're adding 2 edges to it. And you can check that in this case, every edge or every node does indeed have even degree, which means an Eulerian cycle exists. And so here you actually can now travel each edge exactly once, where this edge really is the same edge, but for the purposes of the graph, you can count them as different edges to make sure that you've actually arrived at a solution. Now, in practice, we want to apply this to real data. This is an example of an island in the Philippines, and we make use of 2 primary tools, the first being the hot export tool, which James will talk about in more detail later, but which basically allows us to obtain data sets corresponding to the streets in a given region. And then a second important tool is the NetworkX Python package, which allows us to abstract CSV functions into graphs and then perform this analysis. So this is basically an overview of the initial workflow, where we have a map, where we have a region of interest. We convert it using a CSV into a graph. And then, as I mentioned before, for vehicle routing, you're only interested in connected graphs because notably, you can only drive along streets that actually exist. We have to exclude some of these, extraneous islands or other points that are not reachable from the larger graph. So we obtain what is called the largest connected subgraph, which is, what we're going to be interested in a particular vehicle strip. Now, again, notably, so far we've only been looking at, this is just concerned with basically one vehicle so far. And then additionally, we also have to consider the fact that some streets are one way. But it turns out generalizing the general discussion of the algorithm actually translates pretty simply to directed graphs, where we basically consider edges as two types. We have in edges and out edges for any given node. And then by treating each of those separately, you actually can apply basically the same algorithm and obtain your solution. I think you're muted, James.
So I will be going over the OpenStreetMap routing workflow. So the requirements are to have a given PBF file, and a PBF file is a OpenStreetMap file that is condensed, and you are able to download it from the hot export tool. And we also need to make sure that the program and code is also downloaded on the computer. So to start off, we have a PBF file, and then we want to convert it into a CSV file. And we use a package from GitHub that is able to efficiently convert a PBF OSM file into a CSV file that has nodes in one section and also edges in one section. Next, we take the given outputted nodes and edges CSV files into a condensed edge list. And after that, we want to do some post processing where, as Zade mentioned, we want to find the largest connected subgraph to remove any of the extraneous nodes that may not be reachable. And then we want to then use the condensed edge list as an input to solve for the final route. And we also use another GitHub package that was able to do this very efficiently. So this flowchart is a summary of what I just described in the last slide. And instead of manually inputting commands and making sure that everything is up to date, we can use bash scripting in Linux that can streamline the workflow. So for example, we might need to compile a certain program, for example, the route inspection program. And instead of manually inputting the compiler arguments, we can just simply use a bash script that can abstract the minor details from the user. And so from this, we can reduce the user commands from possibly many to just only one, and that is just running the bash script itself. And we still need to make sure that we have a given PBF file. And from there, we can, you can input a PBF file into the bash script and it will run it from there. So we had some open issues and questions. Right now, Zade is able to get a connected graph from the network X package, but we are still finding a way to possibly crosstalk it with the workflow that we have currently. And one possibility is maybe using disjoint sets. And another issue is large data sets may take longer and more memory to execute due to time complexity. So the Chinese postman problem is, I believe, O of n squared. And this means that it's possible that if we have very large nodes, for example, 20,000, this can take almost up to minutes or hours, sorry, seconds or minutes. and this can slow down the efficiency of trying to find a optimal route.
Notably for preparedness mapping, the issue of time complexity isn't a major obstacle until you get to really egregious times. But if you're working in a very, densely routed area, it is possible then to even go into the hours or possibly days, which is something to think about because you want your software to be usable, obviously for more than just simple data sets.
Yeah, so moving forward, as I mentioned before, we wanted to find or implement a largest subgraph function to find the connected subgraph. And I mentioned using a network_x Python package that Zade was using, and also finding a way to implement a union find disjoint set data structure. Also, next, we want to keep using the hot export tool to download PBF files for extensive testing and debugging. And we so far have 2 large data sets, and we are hoping to download more from the hot export tool. And also, we want to create a visual representation of the route as a supplementary information to just having a text file. So currently, the route inspection problem GitHub package that we are using only exports the route as a text file, and we want to find a way to maybe display that information onto a graph so that it would be easier for users to use. So these are just a summary of the external packages that we use. The first one describes converting a PBF to a CSV file. The second one describes the computational work for the route inspection problem. And then the third one is Zade's use of the Python package to display a graph.
And with that, we're happy to answer any questions or to go in further detail anywhere where somebody might have wanted us to elaborate more.
So I'd just like to lead off by saying thank you so much. That's really fantastic, all the work that you've been doing. I have not been a very terrific manager, and so this is the first time I've seen a lot of the work, and you all didn't disappoint. It's really fantastic to see how far you've taken a very kind of basic prompt and the level of detail to which you've explored this. Some interesting opportunities around like making the end output more usable for somebody like driving a car. And I think a lot of interesting opportunities to explore some individual aspects in more depth, like you were talking about weighting the different edges of a route or of a network, and thinking about like, oh, like we could weight areas with houses near the roads like higher if we're interested in doing kind of an assessment, because if it's a road with nothing there, like there's no reason to capture pictures. I'll go ahead and open it up to the group for questions. Feel free to unmute, or you can type a question into the chat.
Hey, this is Dale. My question really is, Zade and James, this is really awesome work as somebody who's been doing this kind of stuff for a long time. You're done some really, really cool work, so thanks for that. I guess my first question is sort of the time, right? So like in thinking about my own experience in Panama City when we like literally made the decision, went and bought the cameras at Best Buy, and then sent volunteers out the next morning. Like, is it fast enough? Is this process fast enough to be either now or sort of maybe with a little bit more work in the future, be able to sort of to do that kind of like, hey, this is your job today, this is your job tomorrow kind of thing?
Right. Yeah. So, I mean, it's an interesting trade-off because on the one hand, for preparedness mapping, you would want to get the best route possible, you know, assuming that the time it takes for the vehicles to travel might be more valuable than the amount of time it takes to actually get the route. That's not always the case, as you mentioned, especially in cases where you might have, you know, an emergent problem where you actually need a result quickly. And then it becomes a trade-off of, okay, do we, because there are heuristics to get a faster solution, which will end up just being a bit less optimal. And it's going to really be a case-by-case basis where, you know, in some cases, okay, the car will just spend an extra 10 minutes on the road, and in exchange for that, you know, we can get a solution much more quickly. You know, in some cases, if that's worth it, then it is possible, but it's just going to be, it's just a bit of, it's a bit tricky to sort of figure out, you know, when we want to do that and when we want to spend the time to just get the best solution possible. But that'll just, I guess, depend on, you know, a given scenario, whether we're mapping for well ahead of time or whether we need, you know, a map soon. But yeah, there are heuristics that make it possible to get, you know, a map in minutes. It's just a question of whether you're okay with the reduced optimization.
Yeah, as Zade mentioned, I was also talking about a heuristic that we used specifically, or that we were researching specifically, and it's called insertion of a city in an insertion of near a city. And this heuristic describes like inserting a node into the route so that the distance between the two adjacent nodes is at a minimum. And I've done a little bit of testing myself with this, and it was, the final route was very close to the optimal solution, although it was not optimal. And in addition to that, we also have to consider whether like whether the roads are like whether we can actually take that road, if there's any restrictions with that road that might need to be considered as well when we implement this.
That's very cool. Thank you. And then I have one question for Dan, actually. So the final state of this is sort of how Sims mostly works, right? So if we think of, or Sims, or the, you know, when we're able to deploy anybody really again in the future, the idea maybe is that the Sims would support with some sort of graph that would be able to hand off that here, go do this map if you're interested in street level imagery that was produced in DC or London or wherever, right? And then here's a Pelican case with some cameras. Is that what the outcome here that you're hoping for?
I haven't gotten quite that far in the planning yet. In the near term, just combining this with ongoing efforts at how to better utilize street level imagery, whether it's using it for preparedness mapping. And so we want to be able to extract all the features in a city, whether it's street lamps or stoplights and street signs or bus stops, so that we can better map out public transportation or safety for pedestrians or something like that. And also some efforts at disaster mapping, like how can we potentially use street level imagery to analyze impacts on shelter and people's houses. And knowing that like at some point, if we want to scale those efforts, we'll probably need efficient ways to task people to collect the imagery. And so, yeah, just kind of exploring what's possible, and then hopefully being able to dig into the exact workflows and processes a little bit later.
Cool, thanks.
I have a question. I think there's a number of people from the SIMS network, the Surge Information Management Support Network, which is a variety of people around the Red Cross movement, kind of involved in various information management work. If you could like enlist one skill set that's like outside of what kind of the two of you have familiarity with that would help push the project forward, like what would be useful?
Well, I think down the road, if we want to have some sort of a front end for this, neither of us has ever used JavaScript or done, like front end web development. That's a bit a ways away, but I can anticipate that being a hurdle. Either one of us is going to have to learn JavaScript, or it would be nice to have somebody who's more experienced with that. Right now, our main issue is just being able to basically streamline everything. But I think James is being able to figure that out pretty well with his bash scripting. So yeah, I think like somebody who has experience with front end would probably be the most useful skill set right now.
Yeah, I agree with Zade. Right now, most of the bulk of our work is trying to work on the computational side of this problem, and we haven't really considered any user interface or user experience design. So that would be really helpful in the long run.
Great, thanks. Opening it back up to the larger group. Any more questions? I also have a question for the group. If anybody has additional ideas of how this kind of process, this tool might be useful, either uses for street level imagery collected in this way and needing like a comprehensive manner to cover all the streets in a given area, or even outside of collecting imagery, why you might want to have this kind of route calculated for you.
Zade and James, thank you very much for your presentations. Very interesting. I think from the perspective of an example, or where it's useful for, what can be, where we can use it for. With the Beirut explosion in August, we did some damage assessment from the imagery from a pillory. So I think that would be a very interesting use case to see and to make an optimum vehicle routing for that kind of cases. And how, yeah, I think this would be very useful for that.
Thank you.
Hi, Dan. This is Colin. I got a question for the panel.
Go ahead.
Gentlemen, thank you for the presentation. I know this particular work has been centered around, it appears to be more land navigation and kind of traditional routing of streets. I'm wondering if any of this work that you're doing behind the scenes could translate easily into kind of more aerial mapping for helicopter operations. I know the Red Cross movement from time to time in specific situations utilizes the assets of the World Food Program and other type of organizations, but for us to be able to assess and plan how to utilize those specific helicopter drops of humanitarian assistance, if this could, if some tool could be developed to help with logistics planning, forecasting, etc. Any thoughts on that?
Yeah, I will say I'm not exactly familiar with the specifics of helicopter use, but I think in that case, you're more looking at a traveling salesman type problem, because helicopters usually aren't confined to specific streets. So if you have a helicopter and you have a list of destinations you want the helicopter to arrive to, well, then you would have a list of nodes, and you would just want to find, the graph connecting these nodes that has the shortest total distance, if I'm understanding your question correctly. So that's more of a traveling salesman type problem, where our analysis has been mostly focused on route inspection, where we're trying to ensure that we traverse every edge. So James talked about some of the algorithms that exist for traveling salesmen. They're already, I think traveling salesman is much more well studied, and there's a handful of software packages that do traveling salesman for you. But I think you would actually need two quite different types of analyses for the vehicle routing, and then for the helicopters.
Yeah. To add on also, I think the general principle of helicopter routing is very similar to the stuff that we have done. So like an airway passage is possibly similar to just a road on land. And with this, I think that transitioning into maybe doing some more helicopter routing won't be as hard or as difficult as it seems.
Thank you for those insights. And if anybody's interested, I can offer some insights into previous operations, at least from the end user standpoint, that could help inform this discussion going forward. Thank you.
Thanks, Colin. We've got a question in the chat from Matt Merrick asking if there's any links between this work and what informs RCView. RCView is the mapping and data visualization business analytics platform that American Red Cross uses domestically to inform their operations. Yeah, so Dale's work in Panama City, Florida was linked kind of to RCView, and that in the kind of pilot activities we were doing there, we tried some crowdsourcing of the images in terms of analysis, and the surveys that people answered on what was visible in the images, the data went to an Esri platform embedded within RCView. And I think Domestic has some ongoing work looking at how they can use imagery, street level imagery, for their building assessment and damage assessment, looking at different machine learning techniques to extract insights from the images themselves. Christina asks if the, piggybacking on Colin's question, if the same applies to drones. And I'll just answer that. I imagine so, except with that drones are probably more flexible in where you can start and stop, and more limited in the range and how far they can go. And Bernard asks, thank you for such an interesting presentation this morning. It is clear that this could have many applications in a preparedness context. I'm curious if you have any comments about response contexts where routes can be blocked. Think about where a pre-event map might have been available, but this map looks very different after an event, like an earthquake. Perhaps this is a question about how quickly map data can be acquired after an event. Just curious to hear your application discussions.
Yeah, that's a great question. So as I mentioned, we've been using the hide export tool to get our PBF files. You would need some way to get a PBF file, and I'm not sure how quickly those are updated. You know, I imagine they're just not updated in time for a disaster response. But I think a workaround would be, you know, if we're assuming that after a disaster, roads are destroyed and that probably no roads are created, then we could add some sort of functionality where if you had your original graph, maybe you can just remove certain graphs and then rerun the analysis on the updated graph. And I guess that would then give you at least more closely updated, more closely updated graph. I'm trying to think that might take time though if you're rerunning all of the analysis. That's definitely something to think about. You know, some sort of heuristic where if you have the analysis done on the original map, it should be pretty easy to, you know, do the same analysis just on a subsection of the map, or, you know, on a very similar type of map. I'm sure that we can implement some sort of functionality like that down the road. But that's a great question. Yeah.
Yeah. So, for example, if a earthquake happened in a certain spot, maybe we can generate a PBF file of that specific spot. And then we can, like, as Zade mentioned, we might have to add this type of feature, but we can like use that PBF file and then find a way to exclude those nodes from the route, given like the larger PBF file. And that way we can possibly work around like an event.
Right, or even if whoever's in the car just comes across a road that was destroyed, maybe they can just manually say, okay, this road no longer exists, and then they can update. That would probably be easier for the user. But yeah, that's definitely something to think about, and it's definitely very important to include that type of functionality.
And from a OSM standpoint, like one of the kind of strengths and sometimes a challenge with the database is that anybody can update it and the edits are automatically integrated into the main database. So if people are actively editing the map after a disaster, like we should be able to pull that updated road network based on those edits as often as we would like. And additionally, there is some related work if perhaps like there's not good connectivity in the disaster affected area. Like Mapbox has a product for installing a number of their pieces of software on premise that they have also demonstrated how it can be installed on a like an Apple, whatever the small portable hard computer is. And we have the Possum software, portable OpenStreetMap, which is intended to have like an extract from OpenStreetMap installed on an Intel NUC that you can take and access some of your tools kind of offline in a disconnected environment. So there could potentially be opportunities where you run like an extract of the OpenStreetMap infrastructure on a piece of local hardware so that you can manually continue to update that locally and keep your data as closely synced to the real situation as possible as you're working. Rick Steves has a question about the processing power of local hardware. I know that like kind of hardware is getting cheaper and more powerful all the time. What, Zade and James, have you just been running this on your local laptops, or like is this something that really like at some point you need cloud servers to be able to run it efficiently?
I've just been using a Jupyter notebook on my own laptop, and I haven't had any problems. I mean, we're obviously using a pretty small island. Even the graph, it looks pretty complex. This is going to be much simpler than anything that people will probably end up using in the future. But I mean, it took maybe like 2 or 3 seconds to get this type of graph, and then it takes takes less than minutes to do any kind of analysis on it. But so far, I've just been using my laptop. Yeah, I'm not. I mean, maybe if people have access to more computing, then you can get a more optimal solution. So we were talking about earlier, where if you really need a solution quickly, then it helps to have a faster computer, obviously. But so far, nothing has been restricted to where you absolutely need a high processing unit.
So far, the amount of work that we've done only involves a local computer. It doesn't involve any type of external servers. And in addition, I was able to run a 200,000 node data set in like around maybe 30 seconds. So my computer is like 5 years old. So I don't know how good of a measurement that is, but I don't think the amount of work that we are doing requires a computer that has higher that's higher standard and faster in general.
Last call for questions. Okay, thanks again, Zade and James. This was really fantastic presentation, and I'm sure people, as they kind of let this sit, might come up with additional questions or comments. Anybody who has that can feel free to send it to me, and I'll make sure it gets routed to them. Or you can dig through the event invite email list and find their emails there. The presentation was recorded, and so that'll be posted somewhere if you missed the first part or want to share with friends. So thanks so much, everyone, and enjoy the rest of your day.
Thanks.
Thank you.